Okay, welcome back. Same shirt. So here's where we left off the last time. And I'm going to try to clean this up a little bit as we work through this. So we said normally after 1 week of therapy for this elbow problem here, we get an average improvement of 28 degrees. That's, when we're moving our elbow, okay? And what we wanted to do was to administer NSAIDs, some kind of non-steroidal anti-inflammatory, and see if that didn't affect, if we could see if it affected the treatment, okay? So we set up our Null Hypothesis, which said that the NSAIDs, if we use NSAIDs, we're going to get the same kind of improvement. We set up our alternative hypothesis that we're going to see some difference. Okay, we kept with the same criteria for making our decision eventually. Then we collected the data, okay? So we're going to compare this number, 34.56, that's the average for our 9 people that got the treatment. We're going to compare that to 29. And so the first 2 steps were the same as before. Step 3 was similar, and we could sort of start to set up our z-score, right? We can start to set this up. We have the 2 numbers on the top. This is the average for our treated group. This is what we see normally, okay? So there's about, what, a 5.5 degree difference there. The question was, how do we get to our standard error in this case? This is the normal way we get to standard error. But as I talked about in the last video, the problem is we don't have this sigma. We don't have this sigma. That is this measure of variability from our normally treated group. Okay, when we give them the normal therapy. So what we came up with was this notion of using the standard deviation for our sample as a guess for the standard deviation of the normal treatment that we usually see. And we had to make an assumption. We had to make an assumption that compared to, this is treatment that the people normally get. Compared to that, if we see a treatment, we see that the curve just shifts to the right or shifts to the left, that the variability doesn't change, okay? The mean for the treatment here, for our NSAIDs, might be different, but the variability doesn't change. So we said, well, let's look at this measure of variability for our treated group, and we came up with 4.32. So we're going to make that as our guess, except here's the problem. When we do our sampling distribution of sample standard deviations, what ends up happening is sample variability tends to underestimate the population variability. Sample variability tends to underestimate, okay? So this value of 4.32 that we calculated from our sample of 9 people, we know that that tends to underestimate the underlying, the canvas bag population. And so what we're going to do in this case is we're going to adjust that. So this is our bias estimate. This is our unbiased estimate. That is, we expect this to be closer to the overall standard deviation than this is. Standard deviation for our sample. This is our estimated standard deviation for the population. That is, S becomes our guess for sigma. S becomes our guess for sigma. S becomes our guess. Okay? So sort of 2 things that we're doing. We're making an assumption, that the treatment just changes the curve position, but it doesn't change the variability. And then we know that when we do sample variability, it tends to underestimate population variability. So S becomes our guess for sigma, okay? So if we go back to the original here, okay, this is why I wanted to ask you, if you had that sigma, could we do this problem? And the answer is, yeah, you could. This is just our normal z-score, okay? So we pick up here. This is our estimate for sigma. And what we're going to do is we're still going to make this conversion, okay? So here's our z-score. Oh, these pens are starting to get a little funky. The mean for our sample, in this case our NSAID sample, we're going to compare that. This is the population mu. This is the based on samples of 9. So this is the mean for our distribution of sample means, what we see normally. This is standard error. So we get that from standard deviation divided by the square root of n, okay? Before we were given this number. Now we have to generate that number, okay? So what we're going to do in this case is get our S. S becomes our guess. So standard deviation of our sample, in this case the NSAID sample, divided by n minus 1 in this case. That's also known as the degrees of freedom, okay? Make sure we take the square root, okay? This is our guess for sigma. So now we do this additional step. I mean, it's the same as what we did here, but additional to what we're doing. This is S divided by the square root of n, okay? Now, one of the questions that always comes up is, you know, do we need to subtract n from this? And the answer is no, 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 no. This is the new step. Once you get this, you treat it as if it was sigma. Once you get this, you treat it as if it was sigma, okay? Over here, when we had sigma, we divided by the square root of n to get sigma sub m. So we get S. This becomes, S is our guess for, guess for sigma, okay? So this becomes like sigma, and to get sigma sub m, we got to divide by square root of n. So you don't do the subtraction here. There's no need to make the adjustment. We've made it here. Once you make the adjustment, now you proceed like you would here, okay? And then up here, what we're going to do is we're going to do m for the NSAID group. Okay, how much did they improve? Compare, that's subtraction. Okay, subtraction is comparison. Compare it to what we see normally, and now divide by S sub m. So it's the same format. It's the exact same format of our statistic, but it's based on an estimation for sigma. This is when we have sigma, okay? So sigma is given, then you just do this and this. This is our guess for sigma. Now do this and this, okay? And this, since it's based on an estimation of sigma, this is a sigma that we know. This is an estimation of sigma, okay? So sigma sub m, s sub m. Sigma, s. So we get it here, okay? This is when sigma is given. This is when we don't have it. And it's much more common, much more common in research that we're not going to be given it. So this is a much more common statistic. It's of the same form. Make the comparison of the difference. Put that in terms of the variability. Comparison of the difference, put it in terms of variability. I will talk about this more in upcoming classes, but what we're really doing is always, or most of the time, we're looking at difference over variability. Okay? Difference over variability. We're looking at the difference between two numbers, but we always need to compare that to standard deviation. Same thing we did with z-scores for single individuals, z-scores for samples. Now we're doing this with samples where we have to guess what the sigma is. We're going to call this a t-test, so this becomes a t-test instead of a z-test. It becomes a t-test instead of a z-test. Okay? So, oh my goodness, can we do this? Here's what we were given. We had to estimate this standard deviation now. Set up your hypotheses. You've already done that. Okay, this is review. Do your criteria. We've already done that. Calculate your statistics. This is when we got into a little bit of messiness, right? We're going to go back through here. We're going to go back through here. Oh my goodness. Here's the formula. When you're not given sigma, then you need to estimate it. S is our guess for sigma. It becomes, when we use degrees of freedom, n minus 1, we've adjusted so that instead of a bias estimate, it's an unbiased estimate. That's what they're talking about in chapter 4 when they talk about an unbiased estimate. Okay? All right, so let's finish the problem now. Let's finish the problem. Okay? Oops. Oh, that's okay. So now we have a t value, which is my NSAID sample compared to what we usually see, divided by S sub m, okay? So the t is 34.56 minus 29, okay? That's the comparison. How did our treatment group do compared to what we normally see? Let's look for that S sub m. Let's look for the S sub m here. Okay, so our S was 4.59. 4.59 now divided by the square root of 9. I'm not going to subtract 1, okay? I'm not going to subtract 1 in that case. And my, sorry. All right. So my S sub m is 1.53. Okay, 1.53. 1.53, and so my t value is equal to, let's see, my t value is equal to 3.63. 3.63, okay? Now let's not get lost, okay? Try not to get lost here. What does a z-score tell you? A z-score tells you how many standard deviations away from the mean you are, right? That's for an individual score. When we're talking about z-scores for sample, it tells you how many standard errors away from the mean you are, okay? This is the same thing. This is the same format. It's the same format, okay? The only thing is this is an estimated standard error rather than knowing it. It's not been given to us, but this is our best guess. So a t of 3.63, that means that this difference is 3.63 of these. Okay, this is basic math, but people forget about it because you're just punching things into a calculator and you forget, right? The difference between these two is 3.63 estimated standard errors. 3.63 standard errors from the mean. Wow. So before we did our observed z-score and we compared it to 1.96, right? And we made a decision about the null. If we compare this to 1.96, wow, that's way out, right? That's way out there. So I'm thinking that we're going to reject the null. But we have to do one more thing, okay? Because this is not a z-score, this is a t-score. So when we look at, remember we had our alpha level of 0.05. That was a z of plus or minus 1.96. And remember what that means. That means if our sample, if our research sample falls in here or here, we would reject the null because it doesn't look like it's normal, okay? This should be review. Take a moment and think about it, right? Alpha of 0.05 is extreme 5%. If our z-score falls in out here, we reject the null. We're going to do the same thing with t, except, okay, except when we look for critical t is what we're going to call it. So the critical t value, this is, we didn't do this before, but this would be the critical z value. Okay, it's normally just not called the critical z. Now we're going to do critical t. Okay, instead of 1.96, this changes a little bit. Okay, now this is where you need your book. So I'm going to give you a minute to get your book. And we're going to look in the back of the book at the appendices and, what is it, appendix B2, okay, appendix B2. And I know I'm not going to be able to put this up on the screen, but, you know, that's what it looks like, appendix B2. And you'll see it says this is the t distribution. This is the t distribution. So open up your book. With this edition of the book, it's on page 729. But let's give you a minute to find that t distribution in your appendix. It should be table B2 in the back of your book. Okay? Now, let's see if you can read this table, all right? On the far left-hand column, there's a column it says DF. That's your degrees of freedom, okay? Now, in our case, degrees of freedom for this research study was 9 minus 1, so the degrees of freedom is 8. Let's find 8 in the degrees of freedom. Everybody with me? So now I'm going to go across, okay, I'm going to go across the row. What do I want in the two tails? I want 5% in the two tails, okay? I want 5% in the two tails. That's what alpha of 0.05 is. So let's get degrees of freedom of 8. Everybody with me? Okay. 8 degrees of freedom. I'm going to go across until I get to the proportion in two tails combined. The proportion in two tails combined is 0.05. Okay. Everybody with me? 8 degrees of freedom. I'm going to go across the row till I see proportion in two tails combined of 0.05. So that gives me a value, and I'm going to put 8 here as a subscript. I'm going to put 8 as a subscript on my t. Critical value for t with 8 degrees of freedom. Critical value for t with 8 degrees of freedom. Everybody see it? 2.306. Okay, and of course that's plus and minus 2.306. So that's the number. That's the number that's like the z of 1.96. Excuse me. It's like a z of 1.96. This is the number that we're going to use to reject or fail to reject our null hypothesis. Okay? Now, let me explain this briefly. So, when we use an estimated standard error, that is, it's based on our estimated standard deviation, okay? That unbiased estimate. When we use this, what happens is how good our guess is, I mean, this is our guess, but how good that guess is will depend on how many people we've studied. So we're going to have a better guess if we have 20 people in our sample than if we had 12 people in a sample. We're going to have a better guess with 12 people than we are with 9 people. We're going to even have a better guess if we have 36 people instead of 20 people, okay? To the extreme that if we have all of the population, if we have the entire population, we don't have to guess at anything, right? If we have the entire population, I don't need to make a guess. Well, these populations are hypothetical, and so if we had everybody, that would mean our degrees of freedom is infinite. And let's look at table B2 again. Let's look at table B2. Is there degrees of freedom for infinity? That is, if we have everybody. Well, let's take a look. It gets larger, 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 larger. Well, I see infinity at the bottom of the page, right? It would be impossible to have this. But if we have infinity, let's go across till we see proportion in two tails. What's the value? 1.96. Okay? If we don't have to guess, t is z. But when we have less than infinity, that means that the t distribution gets a little bit more variable, gets a little bit flatter, gets a little bit more variable, gets a little bit flatter. Let's look at the critical values. I'm going back to the table. We can learn something from the table, folks. Don't just use the table. It's like, okay, look this up, make my decision. If we start at the bottom of that 4th column over, 5th if you include the degrees of freedom, right? 4th column over, 1.96 at the bottom, right? As we have fewer than infinity, all of a sudden our t value gets larger, 1.98, 2, 2.02, 2.042, 2.045, and so on and so forth. But I really want you to understand that almost all of these numbers in that column are 2 point something. 2 point something, okay? That is, it's bigger than our value of 1.96, but a lot of these values are really close to 2. I'm going to do the math thing again. When you have a ratio like that, this is the power of a ratio of this fraction. What I want to see is that the top is twice as big as the bottom. The top is twice as big as the bottom. That would give me a t value of 2, okay? If the top is 3 times the bottom, then a value of 3. If the top is 4 times the bottom, then a value of 4, okay? It's that relationship here. In this case, the top is 3.63 times the bottom. And if we look up the critical value, still around 2, right? Critical value for the t for 8 degrees of freedom is 2.306. So 2.306, 2.306, right? That's the critical value for T for degrees of freedom, excuse me, for degrees of freedom of 8 for an alpha level of 0.05. We're not going to use this anymore when we're doing T tests. We're going to use the critical value. So you're going to need to know how to use that table, okay? Whatever your degrees of freedom are, find them. Then go across. We want 0.05 in two tails. So in this case, if our data, that is the data from our study, let's keep this straight. This is just the cutoff where we make our decision. Here's what we found. I'm going to compare this to this cutoff. So these people are way out here. These people are way out there. And so the question is, does it look like these people really belong to this distribution? The answer is, it doesn't look like it, that's for sure. They are far out, man, okay? And so what am I going to do with the null hypothesis? What am I going to do with the null hypothesis? I got two decisions, or two options, I should say. We either are going to reject the null, or we're going to fail to reject. And I would say, right, this is 29 degrees. Does this look like it comes from a distribution where 29 degree improvement, right, with my arm, where 29 degree improvement is the mean? The answer is, wow, it certainly doesn't. It looks like it comes from somewhere else, okay? So in this case, we're going to reject the null. Again, why am I rejecting the null? Because our data that we collected from these NSAID people, this number is way outside of our critical region, okay? We're going to say they fall in the extreme. And so we're going to reject the null. Let's go back. Here's the null. That's what we are rejecting based on this value compared to that. Okay, we're rejecting the null, and we're left with this. And I'm saying my NSAID group looks like it's different than 29. Okay, when I give people NSAID, they look like they're doing something different than 29 degrees. That's what the rejection of the null is. Okay? All right. Let's do step 5. Let's do it here. I'm trying to conserve paper a little bit. Okay. I just don't want to run out before the end of the semester. Because I don't want to run out to the store to get paper. I will if I have to, but. Okay, step 5 is our statement. And so this is exciting, I hope. Let's not, we're doing statistics as a tool, but I think this was a pretty cool study, even though I just made it up. It's kind of a cool study. And so let's do this. It appears, and sometimes people get frustrated. It's like, why are you always saying it appears? Well, this is a probability statement. I can't ever say for sure that the treatment worked, but it appears that administration of NSAIDs before physical therapy increases the effectiveness of therapy. Now, in parentheses, let me give you a minute and try to guess what is going to go in these parentheses, right? Because this is not my opinion. So it's based on the data that we collected with these 9 individuals. And so I want to make sure that who's ever consuming my research study in a journal, in a report at a conference, okay? So I'm going to report the t-value now. instead of z, I'm going to report a t value. Okay? I'm going to indicate the degrees of freedom as a subscript. Okay? So this is the t value for 8 with 8 degrees of freedom. Now, when I read this stuff in a journal, or somebody presents at a conference, as soon as they tell me that the degrees of freedom are 8, then I know that they used how many subjects? They used 9 subjects, okay? Because this is the number of people in your sample minus 1. So t with 8 degrees of freedom is equal to, now once again, oh, I want you guys to do this right. I'm always emphasizing this every time I teach this semester. And I don't know, people just don't listen. I'm not going to put my critical value here. I'm making a statement based on the sample that I tested. And so I'm going to show people my data, 3.63. Okay? That's the observed. That's what came from my sample. Semicolon, p less than 0.05. P less than 0.05, close my paren. The period goes after the parentheses. It's one of my pet peeves. I have a whole zoo of pet peeves, okay? The period does not go here. This is part of the sentence. So the period goes here. Period does not go here, okay? And it certainly doesn't go at both places. Parenthetical information is part of this sentence. Okay. Again, let me remind you what this P means. This means that the probability that we would get a t value this high if the treatment did not work, the probability that we get something this high is less than 5%. Or, the shorter version, the probability that the null is true is less than 5%. Now that you know about type 1 and type 2 errors, the probability that we made a type 1 error, the probability of that happening in this case is less than 5%. Remember, type 1 error is when you claim there's a treatment when there really isn't. Okay, it's an error. With these data, that would happen less than 5% of the time. Okay? Boy, I wish I was in class right now with you guys, because I would say questions, people have questions. Do people have questions? Okay. Let's review for a minute, though. This is the only reason that this is different than a Z test. The only reason that this is different. And if you keep this in mind, I think it's going to help you keep your head straight, right? Here's our Z. Now, we did 3 examples of that before. You just finished an exam where you had to do this, okay? So I'm going to assume that you know this stuff. We took our standard deviation, we turned it into a standard error, made our Z. This is of the same form. It's of the same form. Step 1, step 2 are exactly the same. What did we do in step 3 that was different? Right here. This is the difference. That's it, folks. That's it. That's the difference. Okay? This is not different. Even though it's different symbols, we've already done that before. Once you get your S, then you just do the same thing as you did here. S sub n, that goes in here. Get this. Step 1 is making our guess for sigma. Step 2 is our central limit theorem step. We've already done that both places. Okay? This is the new step. This we've already done. This we've already done. Okay? If you can see that similarity, it makes this just so much easier. Okay? It ain't easy, but it's easier than seeing this as something completely different, because it absolutely is not completely different. New step, central limit theorem conversion. We have a t-score instead of a z. Let's see the similarities here. okay? Then we need to adjust our critical value, okay? We need to adjust it because we're making an estimate for sigma. We don't have sigma itself. This is still going to be 2 point something, 2 and some change. It's pretty close to 2, like this was, okay? Which means that the top, in order for us to reject the null, the top has to be more than twice as big as the bottom. The difference has to be more than twice the variability. The difference has to be more than twice the variability, okay? In this case, it was 3.6. This was 3.6 times this. So we reject the null. Here's our t. We reject the null. Step 5 is basically the same. We're reporting a t instead of a z-score. And we tell the reader that this is from 8 people. Okay? So that's the completion of a t statistic. And it's still based on the difference over variability. Okay? Still based on the difference between difference over variability. So let's do another one. Let's do one for homework, okay? I'll set this up. I will let you guys work on this. Of course, there's lots of examples in the book as well. But let's set this up, and I'll let you guys work on it. And then for the next video, I'll start from here, and I'll just go through all the 5 steps, okay? But let me see if you can do it. And again, you might want to watch the video again. This is all in Chapter 9, but you also have to read Section 4.5 in Chapter 4, okay? So let's see, what do we want to do? Okay, let's do this one. Let's assume, I'm going to give you, let's assume that normal heart rate is, let's say the average for the population for heart rate is 74.52 beats per minute, right? Let's assume that to be the case. And maybe I am interested in being a movie producer, okay? And I want to make my movies so people are excited, and I'm thinking about soundtracks, and maybe I want to do some kind of a murder mystery or something like that. And so I'm wondering if I if I have a soundtrack that has a basic tempo that's more, like let's say it's a fast tempo, and I want to see if I can change people's heart rate with my movie, okay? And so I show them the movie with this fast music playing, and I want to see if that increases their heart rate. And let's do this. Let's make this. Let's do this. Let's do a sample of 10 people. Okay, let's do a sample of 10 people. They're going to come in. I'm going to have them watch the film individually because I want to see if the soundtrack is going to affect their heart rate, not the being with other people. Okay, and let's suppose we saw these for the heart rates. Okay, 80, and I'm just making this up. 85, 73, 82, 90, 75, 83, 87, 76, and 89. Okay. Everybody got the numbers? 80, 85, 73, 82, 90, 75, 83, 87, 76, 89. Now I just made this up, so I don't know if it's going to come out to be statistically significant or not. But why don't we leave it here and let's do our 5-step hypothesis test, okay? In fact, let's do, we have time. Let's do the first 2 steps. Let's do the first 2 steps here. So my null hypothesis is that, what do we want to call this? Soundtrack, okay, I don't know, doesn't matter. That soundtrack is going to be equal to what we normally see, normal heart rate. Or the soundtrack is going to be equal to 74.52 beats per minute, okay? Alternative hypothesis is that with the soundtrack, the heartbeat's going to be different than what we normally see, okay? With the soundtrack, heart rate's going to be different than 74.52. Step 1. I mean, this is should be review. This should come easy for you at this point, okay? Step 2. I'm going to use an alpha level of 0.05, okay? You now know, I haven't given you sigma here. I have not given you any sigma. And so without, if we had sigma, this would be a z-score. This would be a z-test, okay? We don't have sigma, and so it ends up being a t-test. We're going to have to use a t-test to do our analysis. So I'm going to do critical t. And now, what are the degrees of freedom that we have here? Remember, degrees of freedom are the number of people we have, number in our sample, minus 1. So the degrees of freedom here is 10 minus 1. So 10 minus 1 is 9. So our critical t-value is going to be plus and minus what value? I'm going to look at my book. Here we go. 9 degrees of freedom. Everybody see it? I'm going to go across. I want 5% in the 2 tails combined. So 2.262. 2.262. Right? So this is analogous to our z-score of 1.96. We have to make the adjustment, 2.262. Okay? This is one of the places where we need to make a little bit of an adjustment. Now we need to do a t-test. Take the mean for our soundtrack, compare it to what we would normally see, divided by S sub m. Okay? So what we need to do for this sample, we need to get the mean for the sample for our soundtrack. We also need to get the standard deviation for our soundtrack, but we start with SS, right? This capital S, capital S. You guys got it? And then we convert to little s. Okay. And I'm going to let you guys do the rest. So we're going to pick up right from here. Let's get these calculations and see if we can get our t-value, make your decision about the null, make your statement about whether or not this soundtrack affected people's heart rate. So we'll pick up on this right from here on Tie-Dye Friday, okay? So I'll see you then. Everybody take care, and email me if you have any questions. But take some time and go through this, read Chapter 9 and Section 4.5 from Chapter 4. You need to read that. Okay, that section will inform what we're doing here. And I'll see you on Tie-Dye Friday.